Tonight, we're going to talk a little bit about trusses and rafters. We run across them all the time, of course, but do we really pay a lot of attention to them as far as how they're constructed and what function they serve? We're going to cover that a little bit. Let's start with the purpose. What's the point of them? Well, they're going to carry a load, and you want to have that load transferred to the ground without affecting the building. Otherwise, it'll just collapse. And that's why engineers design these things. Now, when we're dealing with rafters, we're dealing with the strength and the ability of the wood itself, the individual pieces of wood themselves, to do the job they're designed to do. But when we're dealing with trusses, we're taking a lot of undersized pieces and engineering them in such a way that they will stiffen each other to the point where they act as one piece of lumber. So a truss can actually be viewed that way because it's designed to act like one piece of lumber. Why is that impressive? Well, you can take a 2x4 or a group of 2x4s and make it act like a 2x12, for example. And that's pretty good. Also saves on lumber. So let's talk about that. Now, the primary design of any truss or rafter, or any kind of framing for that matter, is to support any live and dead loads and transfer those loads to the ground where they dissipate into the soil till they reach a null point of 0. That's going to be someplace in the ground. We don't care. Once it's past our foundation, it's out of mind. Rafter ties. When you have rafters, you have to have some way to hold them together because they are at an angle, or they create a triangle in the attic. And if you put a load on top, that triangle wants to spread out, push the outer walls out. And there has to be some way to prevent that or minimize that from happening. That's where rafter ties, also known as collar ties, comes in. It holds the left and right rafter together. And rafter ties are usually found in the upper third of the length of the rafter. So if you've got a 10-foot rafter, or all the rafters are 10 feet, then the collar tie will be within the upper 4 feet of that rafter. Rafter ties can have a central piece of lumber it connects to, and they just connect to each other, depending on the time period the house was built. And they're usually found in every second set. They're not usually on every set, usually every second set. You will run across houses where they put them in every third set and sometimes in every fourth set. But the conventional wisdom for these is they go in every other set. That's where you get the stiffness required to hold the rafters together. Now, in this case, because they're going to be exposed, they're not covered up, they went ahead and meticulously put a collar tie on every pair of rafters. And that's just for looks, for function. And it looks pretty good. Some terminology to know about. You want the ridge vent, the ridge dimensional lumber to be slightly larger than the rafters are, because when you cut a rafter at an angle, you cut a 2x6 or a 2x4 rafter at an angle, and that angle cut's going to be larger than 3.5 or 5.5 inches. So you need your ridge vent to be large enough to handle that rafter to sit completely onto that wood without any of it hanging down. No heels, in other words. Common rafters are rafters that go from the ridge to the wall. On the wall, they cut a notch in the rafter called a bird's mouth to allow it to sit flat so it can be secured better. And there's an example right there of our collar tie. Now, in this case, they're showing a collar tie for an example, but because we have ceiling joists that run perpendicular to the rafter, you really don't need collar ties, because the ceiling joist is what's going to hold it together, and that's going to act as a collar tie. So it's a combination job in this case. If, on the other hand, your ceiling joists run perpendicular to your rafters, that's where ridge vents come in. That's where collar ties come in. The idea of roof trusses came about around the 1950s, depending on what part of the country you're from. Prior to that, most construction was stick frame with rafters in the attic. And with that came rafter ties, bird's mouths, toe nailing, purlins, knee walls, ridge rafters, jacks, and all these other terms that we don't really use a lot anymore because trusses have kind of taken over the business. Remember, roof sheathing or plywood was not commonly used and hardly heard of until the mid to late 1950s. It really took off in the 1960s because of economics. It was just less expensive. I know it's hard to believe in today's day and age when you're talking $50, $60 for a sheet of plywood, but in the 1960s, it ran more like $10 a sheet. So it was economically more feasible to use plywood instead of lumber on your roof. Cost of lumber and the waste produced from construction drove a market of economizing by utilizing more of the tree at less of the cost. When's the last time, for example, you saw a straight 20-foot 2x4? They're rare these days. They were common back then, however. Through engineering, one could take short pieces of 2x4, normally throwaway lumber, and assemble them to carry a load much greater than if the 2x4s are used individually. The early years of trusses were experimental. Initially, 2x4s were spruce pine fir #2 grade. I know they use that a lot in framing today, but trusses typically are going to be built with yellow pine. Even though it's a soft wood, it's actually a very dense soft wood, which is the favorite for truss engineers to use in trusses. And of course, they assemble those pieces once they lay them out. They assemble them with gussets or gang plates. On early years, they used staples, not a smart move. Again, it was driven by economics, and they learned the hard way that staples really don't work. A lot of trusses back in the early days were built on site. Here's a good example of a house that was built. They used plywood sheets as plywood pieces as gusset plates and nailed it a lot. Doesn't have the same holding ability as what they use today, but it probably served its purpose in its day. This house was built in 1967 and probably by the current or the former owners. Trusses create null points that allow for greater load capacity using smaller dimensional lumber, as I mentioned a minute ago. Null points are support intersections that neutralize loads via tension and compression using triangular shapes. Tension and compression are two important words when we're talking about trusses, because what you're trying to do in the engineering of the truss is to zeroize or null the tension and the compression that's created when a load is put on the truss. And that gives it the ability to do its job. Trusses, however, rely on the strength of the lumber itself and what its capabilities are. Tension, compression, bendability, and species of lumber all come into play. But like I said, yellow pine is the favorite probably throughout the United States and Canada. It's rare, but sometimes manufacturers screw it up. It's not always caught by the contractor. That's where we come in as home inspectors, spotting structural issues that may affect a home and a purchase. A little bit more terminology, roof slope, and that's the difference. It's a ratio. It's the difference between the horizontal direction, the horizontal length versus the vertical height. Whereas roof pitch is measured in degrees, 10 degrees, 12 degrees, 20 degrees. 10 degrees closely relates to a ratio of about 212, which by definition creates a pretty much of a flat roof, even though there's slight pitch to it. That's considered a flat roof in most municipalities. And that's going to affect what kind of roofing cover is going to be accepted. We have top cords, we have bottom cords, and we have webbing. And the webbing is the lumber that goes between the top cord and the bottom cord. And you can see here that there are gang plates connecting all those loose pieces, creating triangles, so that when you load up the truss, that load is going to be distributed throughout those small pieces down to the bottom cord and then to the outer walls. And then, as I showed you in the first slide, down to the ground where it dissipates to zero. Top cord, bottom cord. Take a look at this little piece right here. That's webbing. When you have a series of trusses running parallel to each other, They're very strong in the parallel direction, but very weak in the perpendicular direction. So you have to have some way of strengthening that or resisting that bendability by putting webbing in or bracing. And we should be looking for it when we're up in attics. Damaged as a result of installation, that should not go unnoticed. It should have been fixed initially. Somebody wasn't paying attention or didn't care, but we should catch it as home inspectors. Even though the house is 20, 30 years old, doesn't matter. That's an important piece of webbing right there. And it needs to be operational. On-site modifications, we see this a lot, especially with ducting being run and other things being run and storage being created. And again, that webbing is important and has an important function. Now, I got to tell you honestly, one truss with one cut web is not going to make a big deal one way or the other, unless you're in a hurricane, then it might. On the other hand, when you have a whole series of these cuts, that's where it becomes serious. So use your judgment accordingly. Here's some webbing and gusset plates that have been damaged and missing. See that a lot in older homes. So how do we determine if a truss is leaning, how much lean it can handle? Well, there's a formula for that. Maximum displacement. What that means is maximum leaning of any truss depending on its depth. Its depth goes from the top to the bottom. So that's where the formula comes in. D represents depth divided by 50, which is 1/2, or a maximum of 2 inches of lean. So we have a leaning truss. And we need to determine how much lean there is. We don't need instruments for this. We can eyeball these pretty much and tell what's going on with them. So we have our truss depth, D, and if the truss depth is 24 inches, it can lean as much as a 1/2 inch, which is half of 24. Oh, I'm sorry, divided by 20 or by 50, which gives us the 1/2 inch. All the way through down to 96 inches, which is 8 feet, I think. That's a pretty big attic. It can lean as much as 2 inches out of plumb and still be acceptable. Anything larger than that, 2 inches is the restricting number. So if you have a 10-foot depth on a truss in the attic, it can only lean 2 inches. Bracing, as I mentioned a minute ago, bracing is important because trusses running perpendicular, the stress on trusses running perpendicular causes them to bend. They have not much strength in that direction. Strength of a truss or any lumbers in the parallel axis only and not the perpendicular axis. That's why bracing is needed, and we should be looking for it. Cantilever trusses. This is improper installation. Happens all the time. Framers can't seem to get the idea that you can't be putting a load on a open piece of lumber like that. It has to be braced in some way. For example, not here, but here or there would work because that's solid lumber right there. Not here where it's going to bend. And truss manufacturers even give us landmarks to show us where to do it. Something I didn't even have in my day of framing. It says there, bearing location right there underneath this lumber, not here. But you got to be able to read. Again, just being held together with 16 penny nails and in the wrong location. Example of a truss repair. If you see a truss repair in an attic that you're in a home you're inspecting, you should be looking very closely at it because 99% of the time they're done wrong. Here's an example of one, an engineered drawing for a truss repair. We have a break here. We have a crack in the top cord, it says. Well, I think I got a blow up actually. We got a crack in the top cord next to the metal gusset. So right here, whenever there's a gusset plate, we're dealing with various pieces of lumber coming together at that point. That's our null point. So we have to incorporate the vertical piece, the horizontal piece, and the diagonal piece. They all had to be tied together with our repair because that's what the gusset plate does. It holds it together. That has to be replaced with a repair. So how do we do that? And what do we do? Well, let's take a look. The engineer says plywood gussets as shown. You have to use 3/4 inch plywood on both sides of the truss with 2 rows of 8-penny nails at 3 inches on center into all truss members. That sounds like a lot of nails. I did the math for you. It actually comes up to 768 nails on each side, total from both sides, encompassing all 3 pieces of those pieces of lumber where the gusset plate would have held them together. You're rarely going to see that. Nobody's going to spend that kind of time doing a repair in an attic, hand nailing that many nails. They just don't do it. Too labor intensive. Take a look at this one. This is a field modification. I'm seeing 1 nail there, and there's probably more nails, but I'm not seeing them. But they did do plywood on both sides. That's good. But they're going to need, because we're dealing with 3 pieces, cultivating and a gusset plate right here, we're going to need about 800 nails in this thing and this one. So that's 1,600 nails. Good luck finding that. Not going to work. Not acceptable. Here, they're just blatantly cut and then tried to fix with some bolts. And, that's not going to work because most truss engineers are going to require, with a break like this, they're going to require a minimum 8-foot piece of 2x4, multiple nailed and done on both sides, not just bolted like they've done here. They thought that bolts were going to be stronger than nails. In this case, that's not true. Again, plywood gussets, 2 pieces of lumber, cultivating in a null point. Probably going to need less than 800 nails, but I would say closer to maybe 500-600 total for each truss.
But shouldn't that piece of plywood be centered on the web?
I'm sorry?
Shouldn't those pieces of plywood be centered on the diagonal web?
Oh, centered on the web. Okay. Strangely enough, the engineers say if you can get your nails in, this doesn't have to be. If you got enough wood overlapping so you can put the proper number of nails in, that's equivalent to having it centered. Does anybody know what these are right here? This happens to be a mobile home. And what they do is they put their trusses on hinges. In other words, these hinges can lay down. That's a pivot point right there. So they can get under bridges and such when they're delivering the house. And then they put the trusses back up and finish it off. So this is a mobile home. Here's an example of original thinking out of the box. I think it's a waste of clamps myself, but no nails, just glue. They put glue in there. Is glue stronger than nails? I don't think anybody's ever tested, but I think Gorilla Glue might work. I wouldn't trust it though. Hose clamps, not good. Hose clamps here, not good. Minimum 8 feet long. Any truss engineer is going to start from that point. Now, if you see a 6-footer and it's centered on the break and it looks like it's half decent, I probably wouldn't make a big deal out of it. I'm not seeing any kind of other movement. But truss engineers are going to call for 8 feet, almost on every break of a webbing. Unless, of course, it's shorter than that, then you're going to go top cord to bottom cord with it, whatever that length is. This represents the loads on the top cord only, but of course, anything you put on the top cord is going to be transferred through the webbing down to the bottom cord, and then from there to the outer walls. So keep that in mind. A rough rule of thumb is most trusses are designed to handle about 40 to 60 pounds per square feet. Plywood sheet is a 4x8, so you multiply that, you get 32 square feet. 32 square feet times 50 pounds per square foot gives you 1,600 pounds. Or 60 pounds gives you 1,920 pounds. That's the kind of load you're going to find on roofs or less, which is why it's important that these trusses and webs be properly done and correctly repaired. In everyday life, you probably don't ever reach those points. But as you all know, we just had Hurricane Erin come through and 150-mile-an-hour winds. And I was in an area where we had a lot of wind, but not a lot of rain. But imagine down south in Fort Myers where they had both of those things over a 24-hour period. We lost power, by the way. And you can see where these 1,600 and 1,920 pounds forces can be very easily met by wind push and pressure. New trusses. Here's a schematic of a brand new truss. It's going to go with the truss package getting delivered to a new house. I did some blowing up for you. We have a top cord live load of 37 pounds a square foot. Now, when I say most trusses are going to be 40 to 60 pounds, it really, a lot of it depends on the design of the truss and what it's going to be used for. If you've got a small truss, you really don't need to meet those loads that you would find in the typical house that's being built. Might be for a shed, for example. Anyway, in this case, it's going to be a top cord live load of 37 pounds and a dead load of 3 pounds. Now, live loads would be things that do not happen every day. I go back to Hurricane Ian again, where we had 150-mile-an-hour winds. That's a live load. That's not something that's sustained on a regular basis. That comes and it goes. And hopefully the building material will handle it. Dead loads, on the other hand, that would be things like shingles. 3 pounds a square foot for shingles. Tile, that's, of course, if you're going to use tile, you have to design more stringently. And the bottom cord live load is 0. And the dead load is going to be 10 pounds a square foot. The dead load would be storage. You go up in an attic and you see engine blocks hanging, concrete tile piled high in the attic. That's not 10 pounds per square foot. That's a lot more than that. That's concentrated load. And I use those examples because I've actually seen that. So for that truss now, a total 50 pounds per square foot is required in the design, specifically for what it's going to be used for. Be careful when you go into attics. You want to look before you leap. Again. And of course, we have a lot of bats down here. They like Florida. Do not disturb. Purlins. Purlins are braces. Well, let me back up for a minute. Most rafters in the old days were going to be typically 2x4, 20 foot, maybe 30 foot, because attics in the old days were a lot steeper. You could like stand up in them typically. So 2x4s, maybe 2x6s. I rarely see 2x8s, but I'm sure they're out there, different parts of the country. And a purlin is designed to take that 20-foot 2x4, for example, that 20-foot rafter, and cut the distance in half so it doesn't sag. That's what a purlin does. So you see here where they've got this horizontal 2x4 across these rafters, and they're taking this 20 feet and they're cutting into 2 10-foot lengths. Where these vertical pieces come down into the insulation, that's not the proper way to put a purlin in it. Purlins the bottoms of the purlins need to terminate on something solid, like a center ridge going through the middle of the ceiling in the house, which oftentimes old houses had. Those can terminate on that, but you just can't have them terminating on ceiling joists or whatever else is underneath this insulation. And the vertical top here where the 2x4 is up against the rafters, you can't have that sitting flat. It has to be on edge because that's just going to bend. So this is a sloppy, improper way for a purlin to be installed. And you should write that up, even though this house may be 60 years old and it looks like it's fairly straight. Tough, not good. That's still not good. Again, purlin. And you see where they ran a 2x4 across the ceiling joist, and then they ran a flat purlin 2x4 across the rafters. Again, that should have been on edge, not flat. And you cannot use your ceiling joist as the load carry. This double 2x8 right here on the left, if it ran perpendicular to the rafters, the Purlin could have terminated on that and that would have been okay. But in fact, it has not done that. This is a good looking Purlin right here, except for the flat 2x4, of course. And of course, we have skip sheathing. You all know what that is. Skip sheathing was used on roofs where you didn't need a solid support to carry the roof cover, whatever it might be. Tile is a good example of that. 5 crimp aluminum is a good example of that. In this case, they decided to take whatever they had off and go with shingles, it looks like. So they went ahead and sheeted the ceiling, sheeted the roof on top of the skip sheathing. It's cheaper than taking it off and then putting their shingles down. Knee wall is a short wall, typically under 3 feet, used to support brace or brace the rafters and timber roof construction. Knee wall, that little 2-foot wall you see on the left there, that's a knee wall. That does not have to terminate on something solid. That can terminate. You can lay this looks like 2x6s. You can lay a 2x6 down on top of your ceiling joists and put that on there, and that's as good as, and serves the same purpose. It takes long rafters and cuts them into sections. So a 20-foot rafter in this case on the roof would be cut into 2 10-foot lengths. And I noticed they have, whoops, sorry. Oh God, what have I done? Well, I was close to the end.